let's talk about partial derivatives for functions on 3 variables. When I was dealing with a function on 2 independent variables, I had 2 partial derivatives, one with respect to x and one with respect to y. It stands to reason that when I have 3 independent variables, I can have a partial with respect to x, y, or z, and the calculations occur the same way. I calculate a partial with respect to x by treating x like a variable and y and z like constants. Partial with respect to y is my variable. I treat both x and z like they're constants. And finally, a partial with respect to z is calculated by treating both x and y like they're constants. In fact, pause the video after I write this next bit down and see if you can calculate these 3 partial derivatives just by treating the other 2 variables like they're constants. Okay. X is my variable, y and z are constants, so y plus z is a constant, cosine of a constant is a constant. The derivative of x times a constant is that constant. That's like taking the derivative of a line. The partial with respect to x is cosine of y plus z. All right, now, the partial with respect to y, both x and z are constants. So I'm going to treat that like a coefficient in front of a cosine. The derivative of cosine is minus sine, so I have that minus x because it's a constant multiple. Y plus z, and I should be thinking chain rule. The derivative of y is 1, and the derivative of z is 0, so I just have that 1 plus 0 hanging out there. Don't even need to write that down. There's my derivative. And the partial with respect to z works out exactly the same way, with the chain rule still just giving me a times 1 because the derivative of z with respect to z is 1. So there we have it. There are my partial derivatives with respect to x, y, and z. This would go on and generalize. If you had a function q equal to f of x, y, z, w, there'd be 4 partial derivatives. And however many independent input variables we have that many possible partial derivatives.